Okay, so the first document I gave you guys was the key learning intentions for the year. And that's what this document is, 2016 Science Learning Intentions. If I was you, I'd pull that out, and because you can make rough notes on it. The key learning intentions are what your cram cards should show. Yes?
Do you mind if I work on that?
Go for it. Yeah. The key learning intentions are basically what your cram cards need to explain. Okay? So if you can have, like for example, you'll notice there's 4 key points, we'll go through them, on radioisotopes. And I think you could probably almost do radioisotopes in one cram card. So let's have a look. So can you draw an electron shell diagram of the first 20 elements? And an electron shell diagram is something like a Bohr diagram. Now the Bohr one is where you show, well, we'll just choose calcium because it's easy to remember, 11 protons, we'll say 11 neutrons, and then you draw the shells, and you pretty much draw the whole thing. Put the electrons in pairs to make it simpler, and go from there. There's an electron shell diagram of the first, well, you should be able to do any of the first 20 elements. Okay? Now, to be able to define atomic mass and of an element, and atomic mass and atomic number. What's the atomic mass? Yep.
Number of protons.
Yeah, number of protons is atomic mass, and the atomic number is. Yep.
Protons plus neutrons.
Protons plus neutrons.
That's mass.
So you got it back to
Oh, sorry.
Atomic mass
is
is
protons plus
protons,
neutrons.
neutrons,
And atomic number is
Oh,
protons.
yeah. Hang on, I'm just reading this. Atomic and mass number. Yeah, atomic number, number of protons, atomic mass, protons plus neutrons. Don't make that mistake. Now, electronic configuration is basically the electrons in each of the shells. So if you look on the back of your sheet, you'll see a reference to EC there on the electron transfer diagram. So again, if we chose sodium as our example, sodium has 2 electrons in the K shell, 8 electrons in the L, and 1 electron in the M. This is as a simple diagram, so the electron configuration is 2, 8, 1. So it just lists which the electron number of each shell is the electron configuration. Okay? Now, to be able to compare the mass and charge of protons, neutrons, and electrons. Protons positive, neutrons neutral, electrons negative. Protons and neutrons are about the same size. How much smaller are electrons?
A lot.
Not a lot. There's a specific number mentioned. It's about slide 4 of the first slideshow. It's about 1/2000th. Okay? Electron size is about 1/2000th. It's a very minor point, but you could be asked about it. Okay? To be able to define an isotope. What's an isotope? Yep.
It's an element that has more neutrons than
That's
the
right.
normal element.
Yeah. An element with a different number of neutrons. Okay? It can have more neutrons or less neutrons than normal, and that is an isotope. And that is related to, there you go, radioisotopes and radioactivity. Okay, to be able to understand that some isotopes are unstable and decay to form stable elements. So that's where we were talking about radioisotopes, and we looked at things like uranium and how they decay down, which is nuclear decay it comes down to. Okay? To understand that during radioactive decay, energy is given off as alpha and beta particles and gamma rays. An alpha particle consists of what? Yeah.
Is it a helium?
It's a helium. 2 protons, 2 neutrons. Zip off out of the nucleus. What about beta? Yep.
It's when a neutron splits and the electron gets flung out.
Yeah, really good. So when a neutron splits into a proton, which stays in the nucleus, and an electron, which zips off. Okay, and finally, gamma radiation is caused when the nucleus is basically shuffling around protons and neutrons, and the number, atomic number and mass number don't change, but it causes gamma radiation to be emitted. and that is highly penetrative and exceedingly dangerous. Now,
Did you say the neutrons and protons are the ones that were moving around?
yeah, the whole nucleus is shuffling. Okay, so numbers don't shift. Now, and you should be able to distinguish between the different types of radiation based on the penetration of materials. We did a question like that. One of the textbook questions was a researcher is looking at some radiation that's been given off from an experiment, and it's been blocked by plastic. And from that, she looked at the speed of the radiation, she looked at what it could penetrate, and she deduced that it was, I think it was beta radiation. So you should be able to do that. Now, reactants and products in chemical reactions. So when you think about chemical equations, you have reactants on the left and then products on the right, just like the Pracky did. Okay? Just quickly, before I go on, is anyone due to be doing the Prac write-up? Oh, okay, you guys need to start that. So, you will need to come here, grab your sheets and start that. I did mention that previously, not the Imogen one, not Kate Douglas. Okay, James. Okay, Oliver. Esther, watch out. Esther, Daniel, 3. You'll need questions. Where's the question? Why am I not seeing them? More than enough there. That's a question sheet there.
Yep.
Heaps of them. Oh, yes. Oh, it's got 2 tables. Well spotted. There you go. So sit down the back and get started on those. Okay. Okay. Now, in a chemical reaction, the key point is that the atoms are not being created, nor are atoms being destroyed, but rather you have a rearrangement of atoms. And that is reflected in the chemical equation. Now, endothermic, exothermic reactions. Okay, which one? Exothermic. What is happening in an exothermic reaction? Yes?
It starts with high energy and it lets all out low energy and the energy drops.
Okay, that's a pretty good explanation. Will was talking about how the bonds start with high energy and in the reactants, and the products have low energy bonds, and so energy is emitted as heat or light. That's all you have to remember. Energy is emitted as heat or light in an exothermic reaction. What's an example of an exothermic reaction? We'll get someone from the back. Yep. Firearms, any type of combustion, an explosion, these would all be exothermic. You can feel the heat coming off them. What's an example of an endothermic reaction? Endothermic, the energy goes into it. I gave you a really good important one. Photosynthesis is the big one. Ice melting is a simple one. The ice melts because energy is being absorbed from the environment and the ice is melting. But photosynthesis is a really good one. Okay. Now, acid-base reactions and neutralization. Okay, how do we define an acid? What is an acid? What do they give to a solution? You put them in water, yes?
A substance that readily donates hydrogen ions.
Yeah, hydrogen ions or protons. It puts those into solution, so all acids will contain hydrogen. What is a base? Yes?
Is it a hydroxide donor?
That's the one. It's a hydroxide donor. It donates hydroxide to solutions. And what happens when you put those two together, and an acid and a base? What would you get?
They neutralise.
They neutralise, but what do you get?
You get water and...
Yeah, you've got two hydrogens and an oxygen will give you water, and that's a neutralisation reaction. We've talked about 3 types of acid reactions. An acid with a base, an acid with a metal, and an acid with what was the third one? Carbonate. That's right. Well done. An acid with a carbonate, and the products that are produced in each. Acid with a base gives you water, Acid with a metal gives you
Salt.
salt and
Hydrogen.
Hydrogen.
Gas.
hydrogen gas. Acid with a carbonate gives you
Salt.
Salt.
Carbon dioxide.
water and carbon dioxide. Well done. Okay, so that's in about that's about the 5th slideshow. I think we've done 7 slideshows. Now, you should be able to give examples of acids and bases. A good example is any citrus fruit is acidic, so any oranges or lemons or things like that. And bases can usually be a bit harder for people to remember. Lime, not garden lime as in the tree, but rather lime, the white powder, is a very, very basic compound. Or a lot of washing powders are basic as well. Okay. Now, the pH scale. What does 7 on the pH scale indicate? Now, yep.
Neutrality.
Yeah, if it's 7, 7 is a neutral substance, like pure water. What is, if something was 1 on the pH scale, would it be acid, basic, or neutral? Yes? Acid, yeah. Or 1 would be a strong acid, a 6 would be a weak acid, an 8 would be a weak base, and 14 would be a strong base. So you need to be able to navigate the pH scale. Okay, now, 3 types of acid-base reactions, we've spoken about that. And you should be able to write word equations for those acid-base reactions. Exactly as we just did in class before. Acid plus a base gives you water. Okay, that sort of thing. Now, to define an ion and ionic bonding, what is an ion? That's cation, anion, ion. Yep.
Is it a element with a charge?
It's an element with a charge. It can be a positive charge, it could be a negative charge. We'll talk about that. Sorry?
Either an atom or a
Oh, yeah, very good point. It could be an atom or a molecule, because you've got a polyatomic ions where they have like sulfate, SO4, 2 minus. Okay, and so that's a key point. And ionic bonding, we will talk about that as well. But briefly, what is ionic bonding? Yeah, Gretchen?
When a non-metal and a non-metal share, a non-metal and a metal, share valency electrons?
Yeah, that's pretty good, and your thinking is correct. It's certainly a non-metal and a metal and a non-metal. I wouldn't use the word share, because in year 10 you do covalent bonding and they literally share electrons. But I know what you're saying. I would say that they transfer electrons between them. In fact, the metal is an electron donor, and the non-metal accepts electrons. That's always the case. And then they stick together. And you don't need to know the force that sticks them together. It's electrostatic attraction. You don't need to know that. You don't need to write it down. But those opposite charges make them stick together. Okay? And this part here is something that students struggled with a little bit. Ionic compounds as crystal structures, like salt. Now, sodium, when it forms an ion, has a 1+ charge, and chlorine, with an ion, has a minus charge. And we draw pictures of that because it's a simple one to draw. But what actually happens is the sodium will attract chlorine all around it. It'll share a little bit of that positive charge with multiple chlorines, and the chlorines will actually attract sodiums all around them,
Like a lattice.
and it becomes a lattice. One of one, one of the other, and so on and so forth. And this builds up into a crystal, and which is what salts do. But as soon as you drop them in water, they dissolve. That attraction is interfered with by the polar molecules of water, and so they just come apart. But if you evaporate the water, they come back together again, which is what you did in your practical. Okay? Now, there you go. Oh, by the way, I should mention, for the assessment, key components that you covered in the practicals can come up in the assessment as well, in the practical portfolio. Okay. Now, ionic bonding, yes. Non-discrete molecules. to draw a simple electronic shell diagrams of simple ions and ionic compounds. Think electron transfer diagrams. If you look on the back of the first periodic table I gave you, you can see there a simple electron transfer diagram of sodium losing one of its electrons and giving it to chlorine. Okay. So now let's see. Yes, and on the second periodic table, a valency table. Now in the test, you're not going to get, you should have two periodic tables. In the test, you're not going to get to take your periodic table. You don't get to take that one. You just get a periodic table if it's needed. And you won't get to take this in either. You'll only maybe get provided a valency table with some ions on it. And you should be able to work out individual atoms, okay, what charges they develop, and we'll talk about that as well. And to write a balanced chemical equation for acid-base reactions, and we're going to talk right now about balancing chemical equations, like that. Okay, day one, you got your periodic table, and we started filling information in it. Hopefully, your periodic table is in pretty good shape. So, I might just do lights. Okay, so there's the periodic table. It's organised by what? How is it organised? Well, okay, it's numbered from 1 to 118. What's the basis of that numbering? Yep.
Atomic number.
Sorry?
Atomic number.
Atomic number, the number of protons. So hydrogen has 1 proton, it's element 1. Helium has 2 protons, element 2. Why are protons important? Why are they significant? Yep.
They define what element it is.
Yes, the number of protons defines what the element is. You can lose electrons and gain electrons all day. It's still an element of gold if that's the element you're starting with. You can lose neutrons and gain neutrons, that's not a problem. But as soon as you change proton number, the element changes. Okay? And so that is why it is significant. So we have the first number, which is the smaller of the two numbers visible there, is the number of protons. What is the second number? For example, with beryllium, we have 4 and 9. What is 9 the number of? Yep.
Number of protons and neutrons.
Number of protons and neutrons. And almost always, in any assessment, exam or test, there's a question which requires you to calculate the number of neutrons. How do you do that?
Take away,
Yeah, Gretchen?
take away the atomic number from the
Yes, or if you want to do it the easy way, big number minus little number. 9 minus 4 equals, there must be 5 neutrons if there are 4 protons. Okay, so that quite typically turns up. And then we have some other small numbers, but you won't have those on your periodic table. Now, how is this periodic table organised? First, we'll start with groups. What are groups in the periodic table? Yes?
The number of valence electrons.
Well, that's what it comes down to. The group number is the number of valence electrons. Are the groups the rows or the columns?
Oh.
Columns. And the ones you should have marked down are these key ones. I had you write down those primary group numbers. Okay. 1, 2, 3, 4, 5, 6, 7, 8. For group 1, 2, 3, 4, 5, 6, 7, 8. And as Kelsey said, it is the number of valence electrons. What does valence electron? What does valency refer to? Or yep.
Like the outer shell having.
Yeah. When we say valence electron, we mean outer shell electrons, and that brings up this idea of shells and electrons being in shells. If groups go down the periodic table, periods must go across. And again, why? It's a difficult question to frame. What do the periods refer to? Yes?
Reactivity.
No, not so much. But that comes. I see where you're coming from now. Okay. Yes.
Is it how many electrons the shell can hold?
Yeah. That's as I said. It's a difficult question to frame. But okay. We'll start with electron shells. You really need to understand the first three shells. What are the names of the first three electron shells? Yes? K, L and M are the first three shells, and the first period is really a reflection of the K shell filling. How many electrons can the K shell hold? Yep?
2.
2. That's right. The K shell can hold 2, and hydrogen has 1 in its K shell, and helium has 2 in its K shells. Do electron shells fill in a random fashion? Or how does filling occur? And think about the chocolate fountain example I gave you. If I had 10 electrons, can I just stick them in any shell? Is that the way they'll go down? Yes. So how do electron shells fill? Yep.
There's a certain amount of electrons that are allowed in each shell.
Yeah, there's a certain number that can fit in each shell, and they always fill from the inner shell out. Yeah, they always fill from the inner shell out. So K can hold 2 electrons. How many can L hold? Yes? 8. And N can hold 18, but 8 is that special number. And what is the significance of this row down here, the blue ones in group 8? What do we call them? They have a specific... Yes?
The noble gas.
They're the noble gases. And why are they special? What holds them apart from other elements? Yeah, Gretchen again?
They have a full valence shell.
Yeah, well...
They're neutral.
Oh, look at that.
Chemically.
I didn't even notice. See, look, I've been asking questions. Look at that. There's a tiny little K there. There's a KL there, KLM. So there you go. It's a reflection of the shells being thick. So I only just noticed that. That's kind of embarrassing. Okay.
It's pretty small.
The noble gases. Now, you are taught early on in chemistry to use the term full outer shell. But it's not really true because, of course, the M shell can hold 18. But we call this the octet rule. Think octopus. The octet rule is one which refers to the noble gases. That particular configuration with 8 electrons in the outer shell is a very, very stable, very stable chemically, that configuration. So the noble gases do not react with anything. They don't share electrons, they don't donate electrons, they don't accept electrons. They don't form gases with another noble gas. So oxygen is O2, for example, but the noble gases don't do that. They're single atom gases. They do not react. And essentially, all of the other atoms in the periodic table would like to have a configuration that's the same as a noble gas. What was it we said about the crying baby? The crying baby slide, on one of the slideshows, there were 2 things that atoms want. And what are they? Yep.
I always want to be electrically neutral.
They want to be electrically neutral. Spelling. And what was the second thing? Yes?
They want to have 8 electrons in their outer shell.
Outer shell,
Like
like a noble gas. Like a noble gas, which is usually 8, but 2 for lithium and beryllium. Lithium and beryllium would really like to just have 2 in that outer shell. These are a driving force, if you like, in chemistry. Electrically neutral, full outer shell. Now, at this time, for example, hydrogen has an atomic number of 1. How many electrons does it have? 1.
Well, unless it's an ion.
Right. Just in this configuration, atomic number 1, number of electrons is 1, so it would be electrically neutral. Helium, atomic number of 2, how many electrons? 2. So, and that is electrically neutral. Lithium, atomic number 3, number of electrons 3, electrically neutral. Beryllium, atomic number 4, 4 protons, 4 electrons, electrically neutral. So in all cases, electrically neutral, but they don't have an outer shell like a noble gas. So they're only halfway to achieving their particular goal. And that's why ions form. Now, you have on your periodic table a couple of arrows in terms of reactivity, you should know that basically that corner down there is the most reactive. And when we say reactive, we're talking about electrons being lost. So most reactive would desperately like to get rid of electrons, and least reactive in the top right corner. Okay, very, very unlikely to react in this corner. Yes?
It shows the diagram of the size relative to the
Yeah,
atoms.
and we talked about diameter. Now you don't need to remember that, but these ones over here will accept electrons, but they will not give electrons. They are highly attractive to electrons. And that's something we didn't put in. And of course, what does the jigger signify? The jigger. Non-metals. Okay, and these non-metals are highly attractive to electrons, whereas these metals over here are highly likely to lose electrons. Now, we just talked about electrical neutrality and having an outer shell like a noble gas. And how can atoms achieve this? Right, the group 1 atoms all share what in common? If you're in group 1, what do you have in common? Yes?
You only have one electron in the outer shell.
There's one electron in the outer shell. The group 2 elements all share what in common? Two electrons in the outer shell, 3 electrons in the outer shell, 4, 5, 6, 7, and of course 8 electrons in the outer shell. Now, the group 1s, in order to get, and we'll just put a little example up, we'll choose an easy one, like sodium is such a common example, and this almost, I would say, would be used in pretty much at least every second or almost every assessment. With sodium, it has 281 electron configuration, or electronic configuration, and it has 1 electron in its outer shell. It's KLM shell. Now, in order to get an outer shell configuration with 8 electrons, sodium would either have to gain 7 electrons or lose 1 electron. Which way is it going to go?
Lose one.
Yeah, losing 1 electron. And of course, sodium will do that, potassium will do that, rubidium will do that, cesium, lithium, even hydrogen will do that. So the group 1 elements are likely to lose an electron and become, and that will give them so they'll have one more proton than they have electrons. And so what charge will they have? If sodium has 11 protons and 10 electrons, what charge does it have? It should either have a positive charge or negative. Yes, Sergio?
Positive.
Yeah, it's going to be a positive 1 plus charge. Okay? Now, if the group 2 hold true, they will lose 2 electrons. And they will, of course, have a 2 plus charge. The group 3 will lose 3 electrons for a 3 plus charge. And the group 5, 6 and 7, 5 has how many electrons in the outer shell? 5. And it's either got to lose 5 electrons or gain 3. Which way is it going to go? Gaining 3. In fact, there's 3 right there. This will gain 3 electrons and get a 3 minus charge. The 6 will gain 2 electrons for a 2 minus charge. The 7 will gain 1 electron for a 1 minus charge. And so, if that happens, these elements will have an electron configuration that's equal to that of a noble gas, so that's great. But then they're not electrically neutral if they carry a charge of 3 minus, 2 minus, or 1 minus, or 1 plus, 2 plus, or 3 plus. So, how is this issue resolved? These two things that you're trying to do. The example that you can have, or is typically used, sodium might have a charge of, well, if sodium is in group 1 and loses 1 electron sodium has a 1 plus charge. And I might jump to a white screen for that. So, if sodium has a, let's see, it's a 2, 8, 1 electron configuration, and chlorine is another common example with an electron configuration of 2, 8, 7 for K, L, and M. K, L, and M. So sodium is a metal, chlorine is a non-metal, and if an electron is transferred, sodium will gain a 1 plus charge, chlorine will gain a 1 minus charge, and what is the charge, if they stick together as opposites tend to do, what is the charge overall that you get from that? And you get neutral. And so what you would have here, in each case, this would have 8 in its outer shell, this would have 8 in its outer shell, electrically neutral, and that is an ionic bond. And you need to understand that. That's critical. Yes?
In the test tomorrow, is that diagram sort of what we should be trying to do? Is that how much
Well,
we
you
need to
need,
do?
that's an electron transfer diagram, but you
Yeah.
need to understand how ionic bonds work. You need to be able to navigate around the periodic table. You should look at group 2 and immediately know that they lose 2 electrons. You should look at group 5 and know that they gain 3 electrons. Yes? You need to be able to work that out from scratch. Remember, the periodic table that you are going to be given contains none of the information that you've written down. You need to be able to look at that and understand it. So the periodic table, hopefully you've taken good notes on it, and it has all of the information that you need so that you can study this, and then you should be able to basically rebuild it if you need to. Now, any other questions about, now that's the basic chemistry, any other questions about that? So the periodic table, yes, Will.
Should we be able to call them cations and anions, or is
Yep.
that not necessary?
You need to understand what a cation is, you need to understand what an anion is. A cation, is that a negative ion? Or yes, Ashley.
Positive.
Positive ion.
That's a good.
Just cat.
And an anion is an example of a negative ion. Okay? So, good. Any other questions about this? Okay, what's our time? We're in good shape. I'll clean this off and we'll cover a little bit more. Okay. So, okay, now in terms of work, there's the slideshow, Introduction to Chemistry. That's where we started. We've already covered the basic concepts. The periodic table, there's an electron transfer diagram for sodium and chlorine again. Okay, there is the crying baby, what atoms want. Okay. Then we have, yes, this is critical. Okay, chemical formulas and naming ionic compounds. Now we've just talked about ionic bonds. Okay. We've just talked about ionic bonds and why that's occurring. An ionic bond is when a metal on the left of the periodic table loses an electron and a non-metal gains an electron, and then they stick together. Now, what you need to be able to do is, there's that second periodic table that you have. You won't be given this. You might be given a valency table like this. This is for the polyatomic ions that have a charge. You'll notice that they're all non-metals. And then, of course, the group 1 and group 2 and group 3 form 3 plus, 2 plus and 1 plus. And 5, 3 minus, 6, 2 minus and 7, 1 minus ions. You need to be able to work that out. And of course, if they're an ion, they end with "ide." and that comes under naming, the naming conventions. Now, let's jump to there. There's the happy duck slide. Okay, obviously unbalanced, huge man, tiny duck, but they're having fun. However, chemistry doesn't work that way. We need to get the charges neutral. Okay, so in a simple example, if you have, what you're basically doing here is working out the chemical formula. And the chemical formula is the formula of a substance effectively when it's neutral, as far as you guys are concerned in Year 9. And so sodium has a 1 plus charge and chlorine has a 1 minus charge. They will cancel out and you'll get a compound. And what's the name of that compound? Sodium chloride. And where does that name come from? The metal, the first part, is always just the name. Sodium, whatever it might be. And the negative anion, if it's a single atom, will have an "ide" ending. So chlorine becomes chloride. Now in our second example, iron will form a 3 plus positive cation. And of course chlorine can only produce a 1 minus negative ion. So in order to become electrically neutral, you need to have 3 chlorine for every 1 ion. And so the overall charge is 3 plus on one side, 3 minus on the other, and you end up with a compound, FeCl3, and the name of that is iron, and again, chloride for you guys. This one over here gets a little more complicated. This is a polyatomic carbonate. You should be able to find the name on the valency table. It has a 2 minus charge, so in order for sodium to neutralise that, for it to balance out in terms of charge, you would need 2 sodium for a 2 plus, 1 carbonate for a 2 minus, so you get Na2CO3, and finally the more complicated, or the most complicated ones you guys will see, is we've got a 3 plus and a 2 minus, so you need 2 of these for a total of 6 plus, 3 of the carbonate for a total of 6 minus, and you end up with Fe2CO3 iron carbonate. Those are the chemical formulas down there, and these ones are reasonably simple. Even this one, not too bad, but remember, the carbonate is a polyatomic ion, so if you have multiple ones of that, you need to use parentheses and write the number down. I have 3 carbonates. There's 1, there's 2, there's 3. You can't put a 3 in front. You can't talk, Oliver. You can't talk, Oliver. You can't. You can't put a 3 in front. You can't put a 3 up the top. And what you cannot do is put something like C309. You can't do that either. Carbonate is CO3, and I have 3 of them. You'll notice in each of the answers, I don't put the charges down. Don't do that. You can't write charges down. That's not part of a chemical equation. The chemical formula. The chemical formula shows you the balanced chemical compound. Now, naming we've talked about already, and I wouldn't be surprised if you see something like that on the assessment, where you should be able to navigate through this particular table and combine different compounds. A 2 plus magnesium with a single chlorine. I would need how many chlorines? 1 minus chlorines to neutralise a 2 plus magnesium. 2, yeah. So you'd end up with MgCl2. Okay, and it goes from there. Okay, and we've certainly spent some time practicing that. That's not a problem. Now, where are we? That's fine, great. That's one thing we haven't done, sorry. I've just realised, just pull that for a second. Let's see. Oh, that's not too bad. You already know that. I can put that back. Okay. Let's see. Balancing chemical equations. There you go. Done there. Now the other thing you need to be able to do is balance chemical equations. And in balancing chemical equations, the key thing is that what you start with on one side, you have to end with on the other side. So if you like, think of this as an equal sign. So if I have 2 plus, I don't know, 3, it's going to be 5. And so whatever happens over this side, it has to balance in the sense of if I have 1 methane, 2 oxygen, maybe just do it that way. 1 methane, 2 oxygen, 2 oxygen consisting of 4 oxygen atoms. If I look over here, there is an oxygen atom, 1, 2, and oxygen atoms here, 3, 4. I have in methane 4 hydrogens, the little white ones, and I have 4 hydrogens. I have 1 carbon, 1 carbon. That is a balanced chemical equation. So students often get confused between making a chemical formula where you balance ionic charge and in balancing a chemical equation. That is a word equation, okay? The reactants are on the left, the products are on the right, and of course the chemical equation is where we use the particular symbols, okay? And we've had some practice working with that. Now finally, the last one we'll try and get through is the idea of isotopes. And an isotope has a change in neutron number, and so in this case these carbons are all carbon. They have 6 protons, but you can see the number of neutrons is different, although in I think one of them they've lost an electron for some weird reason, but anyway. So we have 6 protons in each case, but the number of neutrons differs, and that gives them slightly different qualities. And in the case of a radioisotope, it means the nucleus is unstable, and so you can end up losing particles or electromagnetic radiation, and that is where we get into the 3 that we have here. Alpha radiation, where you're emitting effectively a helium particle. So you need to know speeds, how far they go through, and that atomic number and mass number are reduced in this case. So you'll see here a little helium will zip out, no electrons on it, just protons and neutrons. Okay, moving quite slow, doesn't go very far. In this case, this is the weird one, this is beta decay, where a neutron, where is it? The green neutron loses an electron and it becomes a proton, which is very strange indeed. So your proton number goes up. You go from carbon 14, which has got 6 protons, to nitrogen 14, which has 7 protons. And it is literally a different element at that time. Okay? And so that electron is moving very fast indeed, and it will penetrate further. And of course, gamma radiation, and we talked about this in terms of damage to DNA. Gamma radiation is highly destructive, ionizing radiation. The numbers don't change, 240, 94, 240, 94, but what you end up having, because the nucleus is moving around, is unstable, is it emits very, very high energy electromagnetic radiation, and that will damage DNA. That will pretty much shear through anything right up until you get to thick lead and concrete, and then you're protected from that. Now, the last thing you'll need, half-life. You'll need to know that. You'll need to be able to navigate around it. You should be able to read this type of graph. You should be able to derive half-life. What was half-life again? It should be written up there. If you can read, you should be okay. the rate at which nuclear decay takes place, so that only half as many radioisotopes are present. Okay? So you're going to, the time it takes for half the nuclei to decay. So in the example of radon, at day 0 you have 100 atoms. Because it has a half-life of 4 days, after 4 days you're down to 50. After another 4 days you're down to 25.